Welcome to section 5.2, the binomial probability distribution. In this section, we'll explore how to model outcomes that involve repeating the same experiment multiple times, with only two possible outcomes each time, success or failure. This includes everything from coin flips to product tests to superhero accuracy ratings. We'll define what makes an experiment binomial, learn to calculate exact probabilities, and explore how to summarize those distributions using mean and standard deviation. To qualify as a binomial experiment, a situation must satisfy 5 key criteria. First, there's a fixed number of trials, for example, 10 shots or 20 survey responses. Second, each trial has only 2 outcomes, typically labeled success and failure. It doesn't have to be good or bad, just 2 possibilities. Third, the probability of success remains constant throughout the experiment. Fourth, the trials are independent. One doesn't affect the next. And fifth, we're interested in the number of successes across all trials. One example would be flipping a fair coin 5 times and counting how many heads you get. The binomial model applies when each trial is consistent and separate, like free throws, customer purchases, or even rolling for loot in a game. Let's take a look at some real-world examples where the binomial distribution shows up. A basketball player shoots 10 free throws. We count how many goes in. A die is rolled 20 times, and we count how often it lands on a 6. Even though there are 6 outcomes to the die, we could define a success as rolling a 6, and anything else as a failure. A student guesses on a multiple choice test. Each question is a success or failure. The company sends out 100 emails and tracks whether each is clicked. In the Marvel universe, maybe we're tracking how often Rocket successfully steals a battery out of 10 attempts. And if the success rate is, say, 80%, we can use the binomial distribution to predict how many successful heists to expect. Here's the core formula for calculating the probability of getting exactly X successes in trials. So X or K, go back, there we go. Well, I guess I lost my pen. Let's get it back. Okay. X or K is n factorial divided by k factorial times n minus k factorial. And then that whole thing times p to the k times q to the n minus k. Let's break that down. So this guy and this guy are the same, right? We saw that formula in a previous lesson. CNK is the number of combinations, how many ways we can get X successes out of n trials. So it's calculated using n factorial divided by k factorial n minus k factorial. P is the probability of success, and Q is 1 minus P, or the probability of failure. And then X or K is how many successes we want to calculate the probability for. This formula gives us a precise way to calculate how likely we are to get, say, exactly 4 customers clicking on an ad out of 10, given a known click rate. Let's start with a fun example. Star-Lord fires his blaster and hits the target 70% of the time. If he fires 5 shots, what's the probability he hits exactly 3 times? So we're going to plug into the formula. N is 5, the 5 shots. X is 3, how many successes we want. P is 0.7. So Q is 1 minus P, or 0.3. Now to calculate this guy, we have 5 factorial over 3 factorial, 5 minus 3 factorial. And remember, 5 factorial is 5 times 4 times 3 factorial over 3 factorial times 2 factorial. Those can cancel. 2 factorial is just a 2, so I can divide it with the 4. And I have 5 times 2 over 1, or 10. Okay, so this guy is a 10. 0.7 cubed, right? Because I'm plugging directly in, P to the K. So 0.7 to the third. And then Q, 0.3 to the N minus K, which is 5 minus 3, or 2. And that's 0.09. So if I multiply 10 times 0.343 times 0.09, I get about 0.3087. So there's about a 31% chance he hits exactly 3 of 5 shots. Now, if we wanted to calculate the chance of him hitting at least 3 shots, we'd need to compute and add that probability of 3 plus the probability of 4 plus the probability of 5. We can summarize a binomial distribution using 2 important formulas. The mean, mu, is n times p. The standard deviation, sigma, is the square root of n times p times q. And of course, we need variance to get standard deviation. Let's say that a student guesses on a 100-question multiple choice test with 5 options per question. If there are 5 options, right, then when he randomly guesses, the problem of getting a question right is 1 out of the 5 options, or 0.2. Then mu would be equal to our 100 questions times the probability of the guess. So 100 times 0.2 would be 20. On average, we expect 20 correct answers. Now, sigma would be equal to the square root of 100 times probability of a correct guess times probability of the incorrect guess. So that's going to be about 4. This gives us insight into both the expected performance and how much variation we can expect between students or repeated guesses. Often we want to know the probability of at most or at least a certain number of successes. These are called cumulative probabilities. To calculate the probability of X being less than or equal to some value K, that is up to and including K successes, we sum the probabilities for 0 through K. This is usually done using binomial tables, technology, like on a calculator. You might use the BINOM PDF function or the BINOM CDF function, right? Our probability density and our cumulative density functions. In Excel, you would use a formula like And then you're going to input the K in P and you tell it true. And so we're going to see that formula in a minute. You can also use the complement rule. If you want the probability that X is greater than or equal to, say, 8, you would do 1 minus the probability that X is less than or equal to 7. These shortcuts save time, especially for large N. Let's imagine Hulk is running 10 lab experiments. Each has a 50% chance of success. Maybe it's testing a serum or smashing a gamma reactor. We want to know what's the probability that at least 8 of them succeed. So using the complement rule, the probability that at least 8 succeed is 1 minus the probability that under 7 succeed, right? 7 or less succeed. All right, so we need the probability to fill in there. So we can easily get it using technology. So we're going to jump over to Excel. So let me get out of here. There we go. And let's jump to Excel. And we would just go binomial distribution. All right. So with our problem that we're looking at, right, we have, we want 7 or less successes. The number of trials was he ran 10 tests. And the probability was a 50% chance, so 0.5. And then true if we want it to be cumulative, right? False if not, right? So we're going to say true to get the cumulative in here. And there's our 0.945. So that's what we're filling in right here, right? This probability is 0.945. So we're doing 1 minus, we get 0.055. So there's only a 5.5% chance that 8 or more succeed. This might help Hulk decide if he needs more trials or prepare for failure. Let's wrap it up. A binomial experiment is based on repeated independent trials with 2 outcomes. The binomial formula allows us to calculate the probability of getting exactly X successes. The mean and standard deviation give us an expectation and measure of spread. Cumulative probabilities help us find likelihoods for a range of successes. You'll find this in applications like manufacturing, quality checks, sports statistics, clinical trials, and marketing analytics.